In the previous chapter, we talked mostly about ionic bonding, but we introduced this idea of a covalent bond. That's a bond that results from the sharing of electrons between two atoms. And the smallest example of that we can really think of is the hydrogen atom. Hydrogen atom has one electron and one proton. And so if we bring those together, we would think that the electron of one would repel the electron of the other, and proton-proton would repel, but electron-proton and proton-electron would attract, and it would cancel out. But if the atom arranges itself just right and has the electrons spinning in opposite directions to counteract some of that repulsion, we can find an optimum position for those two atoms to be apart from one another. And at that position, we'll have the most stable configuration. We'll have a bond holding those two atoms roughly in that position. And so we know that protons are going to repel each other. Electrons are going to repel each other. But electron will attract proton, proton will attract electron, and they're going to find the most efficient arrangement they can to form a molecule. And we defined earlier, molecule was the smallest unit of matter for a neutral compound held together by covalent bonds. Now, this graph kind of gives you, in energy terms, the idea that I was talking about earlier. The energy of interaction between two hydrogen atoms that are very, very far apart, say hundreds or thousands or millions of miles apart, would be zero. So out here, at infinite distance apart, we would say that the energy is zero. As we bring those atoms closer together, they'll arrange their subatomic particles, their electrons and protons, in such a way that they will maximize the attractive interactions, what we count as negative energy, minimize the repulsive interactions, until we get to a point where everything is as optimum as it can possibly be. As it turns out, for hydrogen, that's at 0.74 picometers. I'm sorry, at 74 picometers, 0.74 angstroms. If we push them any closer together than that, then the repulsion of the electrons, the repulsion of the two protons, becomes the overriding force, and we reach this point of positive energy. So that is the optimum bond length. This is the amount of energy that is given off by bringing those atoms together, or the amount that it would take to rip them apart. So just to get a little bit of a hint on how we represent some of these things, I've got drawings or formulas for two different molecules here. Ethyl alcohol, that's the alcohol that we find in beverages that are for folks over 21. The formula, if we write the chemical formula, we write C2H6O. Now the way those are arranged is the two carbon atoms are bonded to one another, and one of those is bonded to the oxygen, which is bonded to a hydrogen. And so each of these lines represents a bond, a shared pair of electrons. What makes something an alcohol is to have a carbon with all single bonds around it and an OH attached to that carbon. Now, from a geometric shape standpoint, and we're going to look at this in the lab next week, geometric shape standpoint, the alcohol molecule would form this shape, this kind of bent shape, where each carbon atom has around it a tetrahedron of bonds. Now a little bit more complicated molecule, blood sugar, glucose, and we find this in some fruits and some other things and so on, is a ring of bonded atoms where 5 of those are carbon atoms. One of them is an oxygen atom in the ring. And then each of the carbon atoms, except for the one directly neighboring the oxygen, has an OH on it, and includes a carbon that is off of the ring. But again, since each of these carbons are all single bond carbons, they all have a tetrahedron of bonds around them. So if we were to, and we can work this out in class together, but if I asked you to write the chemical formula for adrenaline, black represents carbon. Notice that bonds can be made that share more than one pair of electrons. Each line represents a pair. We have 6 carbons in the ring, 3 outside the ring, so C9. How many hydrogens do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. C9, H13O3N, if I counted those correctly, and we can double check that in class. Now, one of the main things that we can use some of this ideas for is another way around Hess's law. We can look up the amount of energy that's associated with each kind of bond. Carbon-to-carbon bonds, single bonds, tend to be around 370 some kilojoules per mole. To break this ethane bond, 377. To break this bond, 370. To break this one in butane, which is 4 carbons long, 372. The bond we talked about earlier between hydrogen atoms is 436 kilojoules per mole. And we can look at a chart of all of these, all different kinds of bonds, and find the average bond energy for a particular bond of that type. So carbon to oxygen, single bond, 350. Carbon to oxygen, double bond, 732. Oxygen to oxygen, double bond, 498. So double bonds and triple bonds tend to be a fair amount stronger than most single bonds. The O to O single bond is only 180. And one of the things that I'll show you in class is that these ideas can be used, these numbers can be used to estimate delta H's of reaction if we assume that all of the bonds of the reactants are broken and all of the bonds of the products are formed in the reaction. Use that as our step-by-step approach. Write down positive numbers for all the bonds to be broken, write down negative numbers for all of the bonds to be made, add them up, and we'll get approximately the delta H for that reaction. Now, the other thing that we've got to keep in mind, we keep calling these covalent bonds the result of shared electrons, but they aren't always perfectly shared. Atoms that are more electronegative tend to hog those electrons a little bit closer to themselves. So the electronegativity of an atom is defined as the ability to attract shared electrons in a covalent bond. We ignore, for these kinds of trends, we ignore helium, neon, argon. They don't really have an electronegativity of any kind. But fluorine is the most electronegative atom on the table. Then oxygen. Then a tie between nitrogen and chlorine. Then a tie between carbon and sulfur, with bromine being a little bit higher than carbon and sulfur. And we notice that as we work from right to left and down, the electronegativities get less and less and less. So the most electronegative atoms are up here, the nonmetals, and they're going to hog electrons in covalent bonds. That means they might not become a negative ion, but they're going to have some negative charge to them. And we take a look at that example of that right here. The difference in electronegativity between sodium and chlorine is very, very large. Let's go back and look. Sodium 0.9, chlorine 3.0, so the difference is 2.1. That's a large enough difference that chlorine can just take the electron. And we don't have a covalent bond anymore. We have an ionic bond. But for hydrogen and chlorine, the difference is lower. Hydrogen's 2.1, chlorine is 3.0. The difference is only 0.9. Chlorine's still going to hog the electron a little bit, but not 100%. And we have a polar covalent bond, a bond where the chlorine has a partial negative charge on it, but not a whole negative charge. And that's what this little symbol here stands for. That's a lowercase d, lowercase delta in Greek, and that stands for partial. So partial negative, partial positive. Whereas if chlorine bonds to chlorine, they both have exactly the same electronegativity, and they're going to share the electrons perfectly even between themselves. Now, the next thing we're going to want to be able to do, and we're going to spend quite a bit of time in the next class doing this, next couple of classes perhaps, is be able to represent the kinds of molecules that we're looking at by drawing what we're going to call Lewis structures. And you can read and see some great pictures of Lewis structures in the textbook to help out between now and then. But in order to draw a Lewis structure, we're going to have to follow these rules, and the best way to do this is going to be by example. So we're going to spend quite a bit of time on this in class. The first thing you'll do is add up the number of valence electrons total for the whole molecule. So for example, CH4, hydrogen has 1 valence electron. There's 4 hydrogen, that's 4 valence electrons. Carbon has 4, so that's 8 for the whole molecule. In Lewis structures, we're going to represent each valence electron. A line between two atoms represents a pair of electrons, and a dot represents a single electron, and usually we'll write our dots in pairs. So we'll arrange the atoms in the arrangement we think that they're in, and then draw a line between each atom that's connected, and that will give us each of those lines will represent 2 of the valence electrons that we're allowed to draw. Then to each outer atom, unless it's a hydrogen, we'll add lone pairs to get them up to their octet. If we have any electrons left that we haven't drawn yet, any valence electrons left, we'll put them on the central atom. If we finish this step and the central atom doesn't have its octet yet, if it's still short of an octet, we can pull lone pair electrons off of the outer atoms, not move them to the center, but move them to a bond between the center and the outer atom so that everyone can get the octet rule filled. So that's when we'll draw double and triple bonds, is to finish that octet. And there's some more I want to say about this. I'm going to pick up with this slide in the second video for this chapter.